To introduce the symbolic differentiation feature in HLSL, we examine its utility in three aspects of surface rendering. We begin with simple procedural geometry, mapping a two-dimensional domain onto a three-dimensional surface. For lighting, surface tangents and normal are computed from the partial derivatives of the surface with respect to its parameterization. Because the normal is extracted directly from the surface through differentiation, the surface illumination code remains accurate without modification as the surface is deformed. Here we further modify the surface with an animated procedural displacement map. A noise function offsets the surface along its normal. Symbolic derivatives then determine a new bumped normal for lighting. Surface deformations and texturing remain independent from each other and uncoupled with the shading. While HLSL also offers limited GPU differentiation through the DDX and DDY functions, this side-by-side comparison shows the quality difference. Note the blocky artifacts from the quad-based DDX-DDY derivatives. As a final example, we use symbolic derivatives to anti-alias procedural textures. Projecting the partial derivatives of the pixel position onto the surface gives a metric of the scale of the surface at that position. Higher frequencies of the noise function may then be eliminated based on that scale. We now combine all these effects into a landscape of realistic procedural objects. In addition to the procedural geometry and texturing already demonstrated, these objects employ a distance-based continuous level of detail. The shading code for these models is unaffected by the blend from coarser to finer detailed geometries, and in fact, the automatic extraction of surface orientation through symbolic differentiation allows the lighting code to be decoupled from the surface specification, enhancing code clarity, robustness, and maintainability.